Welcome back to the classroom. I'm Mr. Wong, and today we're going to be going through Module 8 from the universe to the atom, inquiry question 2, structure of the atom, and we're going to look at a specific experiment that looks at the nuclear model of the atom. So we're looking at Geiger-Marsden's experiment, and we're going to look at Rutherford's atomic model. So Rutherford's quite well known and credited for the discovery of the proton, and at least the structure of a positive nucleus. You can check out the textbook references. Those are your page numbers. Just to give you a bit of quick understanding of what's happening so far. We know that in last lesson we talked about a guy called J.J. Thomson, and he came up with this idea of the atom. The concept of you had the sea of electrons embedded in this positive sea of positive charges, reminding you of a plum pudding model. We're going to progress today and look at, from here to here, we look at Rutherford's model of the atom. You can see there is a positive nucleus. Most of that space is now gone, and you have these electrons in orbit. Okay? Now, just to give you a little understanding, J.J. Thomson was the teacher of Ernest Rutherford, give you a bit of context. And then later on, we will talk about in next lesson, this guy here called James Chadwick, and he comes up with the idea, or discovers, the neutron inside the nucleus. Just so we start, we have the hydrogen spectra. So what can we say from the hydrogen spectra if we separate into opposite string charges? Give you a second to figure that out. So the fact that hydrogen can be split into subatomic particles means that the hydrogen atom has different components inside of it. Okay? So those charged particles could be protons, neutrons, electrons, or not neutrons because it's not oppositely charged. But that shows you inside an atom there are smaller components. In the HSC, this is designated as a band 2 to 3 question. And obviously you can see that that's our answer there. Okay, so the first person or first two people I'm going to talk about today is Geiger and Marsden, and they're well known for the gold foil experiment. Now you might have heard of this in year 9 as the Rutherford gold foil experiment. It was actually conducted by his PhD student and also a lab partner of Rutherford's. Okay, so Hans Geiger, he's also known as the inventor of the Geiger counter, so the way we calculate and measure the amount of radioactivity or radioactive decay. We have Ernest Marsden, who was an undergrad student of Ernest Rutherford. And basically, to give you context of what happened, Rutherford told Marsden to investigate alpha particles. Alpha particles, if you remember, is the sort of nucleus of a helium atom. So you have 4 protons, or 2 protons, 2 neutrons. And the idea is to shoot this alpha particle into this densely packed gold foil and see what happens when that interaction occurs. Okay, just to give you a bit of context, like I said, alpha particles have 2 protons and 2 neutrons, and if you say an alpha particle, it's equivalent to saying the nucleus of a helium atom. That means there are no electrons, which also means that a alpha particle has a +2 charge. Okay, +2 charge because it's lacking 2 negative charges. Okay, a lot of radioactive decay does emit alpha particles. This generally happens with the more heavier isotopes. Okay, so there we know helium carrying 2 positive charges. Okay, so just to give you a bit of context, if you have a look at this animation over here, we show the gold foil experiment. So the idea is very simple. You shoot a bunch of alpha particles and you want to see what's happening in this gold foil. Now the original interpretation, remember we're basing this off J.J. Thomson's model. So if J.J. Thomson's model of the atom was correct, you'd have mostly positive charges and you'd have the alpha particle just going straight through, interacting. It might bounce off because of the positive sheets, but what they actually found was this happening here. So the alpha particles, most of them went straight through. That shouldn't be the case because if the atom is a sea of electrons or sea of positive charge, then these alpha particles, being positive themselves, should be repelled. But that's not the case. Every now and then you'll see a bit of deflection, like so, and every now and then the rays actually, or the alpha particles, get reflected backwards. Now what that would imply is there is a positive component of this gold. There's a positive component inside of it. But the fact that 1 in 8,000 of these alpha particles being shot would be reflected or deflected, that would imply that a majority of this particle that we're looking at here, or this chemical, this atom, is actually mostly empty space, and only at a very small fraction of that space is where these positive charges are. Now I did say positive charges, and the reason being is because, like I said, alpha particles are positive. So if you have a positive 2+ charge and you bounce straight back, or you get reflected, remember, same charges oppose each other. So that would imply that the nucleus that it was striking had to also be positive. Okay, so what can we tell from this diagram here? 2 reasons gold was used. Firstly, gold is pretty non-reactive, so that's really useful. The second is gold is one of the densest metals in the world. Okay, if it's really, really dense, that means that the atoms that make up gold are really, really packed together. Now, if you really want to see the interaction with radiation, you want something that you have a high hit rate. So the greater likelihood of you having these alpha particles collide with these nucleus, then that would be great. That's what you want to see. Okay. Now the reason why there was deflection is because the atom had to have had a positive charge. All right. Otherwise, the positive charge of the alpha particle wouldn't bounce back. And also the reason why it's 1 in 8,000, that would suggest that the density of the mass is centered to a very confined space. Okay. So that's what we see here. So if we try and look at the observation to the interpretation, if most alpha particles pass through, like we said, only 1 in 8,000 didn't do so. So that means that 7,990 would. That means the atom is made up of mostly empty space. If some alpha particles were deflected at a small angle, that would imply that our nucleus, or this center point here, was positively charged, and occasionally an alpha particle travels back to the gold foil. So what that would also mean is most of that mass of the nucleus is based there. So densely packed nucleus, and this nucleus will contribute most of the mass of the atom. Okay, that's what we can infer from this observation here. So there's your summary notes there for you to take in. And that's basically what we're saying. The fact that the alpha particle is positive, it will be deflected by the positive nucleus. So what's the actual model that Rutherford contributed to this? Because remember, he didn't do this investigation. He told his students and his assistant to do this for him. And part of your syllabus outcomes is to understand how this experiment was set up. So it might be to your worthwhile to know what he used. They used beta particles, they had a detector, and they had gold foil. You also need to know what happens to the alpha particle as it interacts with the gold foil. Okay, keep that in mind. Okay, so now we look at Rutherford's planetary model. Now, the reason why we call it planetary is because he gave the idea that electrons were in circular motion around the electron, or not electron, the positive nucleus. Okay, so he came up with this idea. Given the fact that there was deflection, he basically inferred that the center, the nucleus, was densely packed with positive charges, which he later called protons. Okay, and that the electrons were just in this sea of ocean outside, going in circular motion. Now there are some, well actually there's a very obvious limitation of this model, which we'll get into. I wonder if you can figure it out yourself. If you have a moving charge, what other thing could we generate? Okay, so densely packed. Now, the reason why the atom is stable, his theory, is because the electrons and the protons are held together by electrostatic force. Now, that's true, but also there's a slight issue with this, and also an issue with the circular motion. When we come up with electron shells, orbits, this is first proposed by Rutherford, but these are just suggestions in the model. There was another fella who helped him sort of sort out what everything was. Okay, so let's kind of evaluate the model and look at some of the issues and why it eventually got replaced. The first thing is location of the protons, we know. We also know that the nucleus is positive. That's great. So those were the achievements of Rutherford's model. Knowing where the nucleus is, or knowing where the mass was, it was densely packed in this arbitrary center point. And we also know that that nucleus was positively charged. But there are limitations. The first one is circular orbits of charged particles. Now, if you might remember a guy called James Maxwell, and Maxwell basically hypothesized in his 4 equations, if you have a changing electric field, you have a changing magnetic field, you get an electromagnetic wave, EMR. Okay, electromagnetic radiation. Here what we have is an electron that's moving. So this moving electron will generate an electric current that's also moving. So that's changing. That electric current will generate, obviously, a changing electric field. The reason why it's changing is because it's accelerating, right? It's going through centripetal motion, circular motion. If we're going through circular motion, we're constantly changing the direction of the electron. So there's acceleration, there's changing direction. According to, who was it that said that? Changing electric fields, you get changing magnetic fields. Okay, that was Faraday. Okay, or was it? It doesn't matter. So that's what we get here. So that was one of the issues. The other issue was, why were these electrons specifically arranged to go in circular orbit? There was no real explanation to that, and there was no real explanation why the electrons had to be outside the nucleus. The other thing was, why doesn't the electrons collide with the nucleus? Now we know that the electrons are negative. We know that the protons are positive. So why, oh why, didn't the electrons get attracted to the protons and just spiral into the center? So why didn't the electrons just go straight in like that? What was the thing that prevented this from happening? That's what we need to know. Yes, so just a quick thing to note. Faraday didn't say that a changing electric field made a magnetic field. That was a different person. It was Maxwell and another equation. Faraday actually said the opposite. Changing magnetic flux generates an EMF. So other way, but either way, still holds true. You have a moving charge. The moving charge has a changing electric field, magnetic field, electromagnetic radiation. So if we're generating electromagnetic radiation, that can't be true, because we know one thing. The one thing is atoms are stable. That's the common feature of atoms. The reason why we have atoms in the universe is because they're stable. If we have this continuous circular motion of electrons, then we have infinite amounts of electromagnetic radiation being produced. That means our atoms will be highly unstable, but we don't see that, so that doesn't match our reality. The other thing is that if you keep having this rotation of electrons, you're going to keep creating a lot of electromagnetic radiation. You're only using a certain amount of kinetic energy to make it rotate. How come you're making all this electromagnetic radiation? The conservation laws don't match up. So this idea, one, it doesn't match up to what Maxwell was saying, and two, it doesn't fit into the law of conservation of energy. And remember, the key thing with physics and a lot of sciences is, if you can't explain it with the law of conservation or conservation laws, it's probably something you need to work on. Okay, so the other thing is this. Now, obviously you know what this is. This is the absorption spectra of hydrogen and the emission spectra of hydrogen. Now, if you look at this model, some of you will already know how these spectras are formed, but at the time, this model, you can't really tell. You can't really tell what's happening with this model that gives you the idea that these specific lines are there. So how could we work it out? Comes another person. Okay, so before we go on to that, let's just quickly recap on the inadequacies of Rutherford's model. Firstly, position of the electrons weren't specified. That's no good. B, address the stability of the atoms if electrons were indeed accelerating. Didn't do that. Again, that's something to look into. And then next one, not explain the hydrogen spectra. And D, didn't explain why the electrons didn't spiral into the nucleus. So there are two things you need to know. One is the actual model of Rutherford's. So draw a diagram, label it, make sure you know which part's which. The second dot point you need to know is what's the limitation of his model, which is this bit here. That is another dot point that I didn't add here, but it's quite relevant in this part as well. So we have a little twist. We have something that can't be answered. But like most things in science, eventually someone will find something and you will find an explanation of it. Luckily enough, he didn't have to wait long. A guy named Johann Balmer. He is actually famous for actually looking at the hydrogen spectra. And actually what we see from the emission of visible light, we actually call this the Balmer series. The Balmer series is actually also the analysis of visible light being emitted by the hydrogen atom. Now, the key point is, with the Balmer series, the idea is you can go from a shell from infinity, or well, really in this case it's 6, so we'll go 6, to N2. So the idea is in that process, the energy gap between N6 to N2, that energy gap is equivalent enough to give you visible light being emitted. Remember, the idea is these electron shells are quantized. So there's a quantized energy level for this. To get from here to here, you need a specific energy released in the form of visible light, in this case, to be released outwards that way. If you actually went from 6 to maybe 1, that actually generates UV light. So keep that in mind, kids. If we're looking at the emission of visible light, it's from N6 to N2. Sometimes they do word it from any number of N to 2. That's an important factor to keep in mind. Okay, so the last guy we're going to talk about is Niels Bohr. And he actually comes up and puts in the ideas of Max Planck into our understanding of the quantum model of the atom. So what you would see here, this is sort of the basic model they talk about in Year 9, Year 10 physics, or not physics, chemistry. The concept of electron shells. Each shell has its own specific number of energy. This is based off this guy here, Niels Bohr. Okay, so what did he actually show for? The atomic structure is very simple. The energy shells are quantized. It has a specific energy. The electrons will orbit this positive nucleus. Okay, so that kind of explains where the positioning is. And the higher orbits, the higher amount of energy they have. So basically you expect them to have a lot more energy when they spiral in the most outer shell. If an electron was to transition from high energy to low energy, so let's say this is our high energy example here, it wants to come here, it's got to release electromagnetic radiation. If this electron wants to come here, it's got to absorb some kind of electromagnetic radiation. Because the energy here and the energy here are different, you need that amount to step up, or you need that amount to relax and come back down to the bottom. So this follows the law of conservation of energy, and you can see where Max Planck's equation really comes in to help us. The energy difference we see can also help us work out the wavelength of light that is required to be absorbed. So the final energy level to the initial, okay? And it also tells us the wavelength of light we produce there too. So Niels Bohr came up with a really ingenious way to explain these Balmer series or these emission spectra that we see here. The idea links back with Planck's constant, he came up with the idea that each energy level is quantized. Remember, quantized means it's a fixed. So each energy level is a fixed number. In order for an electron to migrate up or down, you have to give off that energy difference. Okay, the formula we can use, let's say, because we know for the visible spectra, the electron always needs to migrate to the second energy shell at the end. So it doesn't really matter what initial shell we do, but that's it. So say we go from 5 to 2, we need to subtract the difference in the energy gaps of 5 to 2, and that will tell us the total energy of the electromagnetic wave that's emitted, and that also tells us the frequency and wavelength. Generally speaking, the larger the energy gap, the higher the frequency, as you can see here. So if E2 and EI are a lot bigger in difference, then F will obviously be a lot bigger. That means we will generate much shorter wavelengths of light, which is consistent here. If we look at 6 to 2, that's our sort of violet blue color. If we look at 3 to 2, smaller energy gap, we have a longer wavelength in red light there. So he kind of added on to Rutherford's model of the atom, basically saying that electrons absorb and emit specific quantum of energy to move into a stable energy, that's given there. He also said that electrons are stable in their orbits, so in these circular orbits, they're stable. He doesn't really explain, though, why. And there's another person that's involved before we can explain that. So this is one of the limitations. He hasn't actually explained why circular moving electrons don't emit electromagnetic waves, but that's just one of his 3 postulates. The third postulate is the atom exists in a stable circular orbit. Again, these two don't quite make sense because he hasn't quite explained why a moving electric field or moving charge doesn't produce electromagnetic radiation. Hence, why is the atom so stable? These 2 postulates don't quite explain that, but the important part is he added this component of a quantum electronic energy level. That's the use of his model here. Okay? So what did the hydrogen series provide the Bohr's atom? Well, firstly, the credibility, because at the time, this concept of quantized energy states, that only really could be explained thanks to this Balmer series or the hydrogen emission spectra. Without it, the Bohr's model of the electron shells wouldn't really be able to work, basically. Okay, so that's what we talked about. We talked about Geiger and Marsden. Don't forget, they're the gold foil experiment dudes. Rutherford, he was the one who proposed the concept of the proton and that the atom is made of really densely packed positive charges in the center, and then everywhere around it you have electrons circling around. And then Niels Bohr came in and provided the concept of the electron shell as we know of it today. So that concludes the lesson. Thank you for listening, and you're always welcome back to the classroom. Until next time, keep learning, stay safe, and enjoy.